This is Topic 9 in Unit 1, Measures of Variation. In this topic, we are going to continue on with descriptive statistics, as well as introduce data and some of the initial functions that you would like to be able to do within it. So besides trying to summarize a data set with a single number, which was what we did with measures of center, another important aspect of data is also to understand how spread out your data values are. This will be done with measures of variation. Officially, a measure of variation is a quantity that describes how spread out or scattered a dataset is. All measures of variation are rounded to one more decimal place than the original data, and by definition, all measures of variation are sensitive to outliers. There are a number of different types of measures of variation. We are going to focus on just two of them for now. And those two are range and standard deviation. Other measures of variation that are also popular that we won't be covering are variance and coefficient of variation. We will eventually be returning back and talking about variance a little bit later on in Unit 4. Range is the difference between the maximum and minimum values. It has the same unit as the original data. This is the same range that you probably have experienced in another class. And this is a formula version. Standard deviation is the most popular measure of variation. It is important to report this anytime you do any analysis of a data set. Officially, a standard deviation is a measure that determines the general amount that values deviate from the mean. Standard deviations have the same unit as the original data and is always positive unless all values are the same. In this case, then the standard deviation will be 0. We will find a standard deviation by hand. Typically, it is something that would be done using some kind of technology. But it is important to do this to get an understanding of how standard deviations actually describe data. Also important with this are the symbols that we use for standard deviations. So there's two different ones. There's a standard deviation for a sample, which is the lowercase regular s. And then there's a standard deviation for a population, and this is a Greek lowercase sigma. So it's kind of like an O with a little, line or a loopy on top, depending on who writes it. I do want to point out that although we aren't going to be using the formulas or finding standard deviation by hand more than this initial problem, that the formulas for standard deviation differ for the population and for the sample. So what you might notice for the difference is that the denominator for sample standard deviation is n-1, and the denominator for a population standard deviation is an n. So there's a very technical answer to this as to why that is different. But what you can think about this as is that when you find a standard deviation of a sample, it's not a census, so it is not necessarily going to be exactly the same number as if you were able to do a census and get your whole entire population's information. So typically the sample standard deviation tends to be a little bit smaller than the population standard deviation. So for this reason, you take one away from your sample size and it ends up making the sample standard deviation closer to the population standard deviation. So that explanation is, again, actually very technical. So it's just important to understand that there is a little bit of a difference to make, but you won't be very affected by it in general. So here's an example of two graphs. These are the ages of the Oscar winners divided by actress and actor for, I believe, every winner until 2009 is when this data set stopped. So for the best actress, the mean of this data set is 35.9, so that's right around here, which kind of makes sense because we have a bell-shape-ish kind of hump here, and then we kind of trail out to the right. So this would be, I would describe it as kind of skewed to the right, since our tail is to the right. The standard deviation is 11.1 years. So standard deviation a lot of times can get compared to your mean. That's actually the coefficient of variation that we aren't going to formally be talking about right now. But one thing that you can do is compare standard deviations for similar data sets to each other. So when we look at the histogram for Best Actor, the mean is 44.1, which does make sense. It definitely looks like in general this data set was shifted to the right from the Best Actress. So they had a higher mean, but another thing that you can see from this picture in general is that they're in general more compact values. So the standard deviation for Best Actor is 9, which is a little bit less than Best Actress. And looking at these two data sets, they do seem to have a slightly smaller spread for the actor. So smaller standard deviation, in general, the values are spread out from the middle less. Larger standard deviation, the values are a little bit spread out more from the mean. Variance I do want to include officially on a slide because it's really important in statistics. However, it's kind of weird. So the variance is the standard deviation squared. And so one thing about this is that the units are also going to be squared. So whatever you do to the numbers, the units work the same exact way as well. So in our previous example, if we were dealing with the variance, and our variance was 100, it would be 100 years squared, which is very, it's difficult to understand, if not impossible. So variance is, again, really important, but it's not popular for a number of reasons. However, it is used in a lot of tests and calculations. So we at least need to see it now, so when it comes back up later, it's not a complete surprise. So let's look at an example, and this is also going to get us into introduction to Stata. There will be another video for an introduction to Stata that will go over more specific pieces of it, such as opening Stata, what kind of issues you could run into with data input and other things like that I've seen commonly over the years. So this is an example of the high temperatures for January 25th, 2016 in Casper. So 29, 30, 36, 40, 44, 38, and 38 degrees. Find the range and standard deviation using the calculator. We're going to be actually using Stata, as well as by hand. So you will not be required to find a standard deviation by hand on an exam. But again, we want to see just one so that we can kind of get an understand of what exactly a standard deviation is trying to tell us. The range is straightforward. It's based on the maximum and minimum values, and you find the difference between those two. So in this case, the range of the data is 15 degrees, which means from the lowest high and the highest high, there's a difference of 15 degrees. I think this is actually a pretty large range for wintertime, because, usually in the month of January, you're expecting pretty cold and chilly temperatures most of the time. So I think if today was one temperature and tomorrow was 15 degrees warmer, that would probably be a pretty big difference. So on this next slide, we are going to find the standard deviation by hand. And again, this is not something that you are going to be personally responsible for on an exam. However, I do think it is really important in understanding how to interpret a standard deviation. So if you look at this table and it is very intimidating to you, I would recommend following along, but not necessarily trying to reproduce it on your own. However, I do think it is helpful to find at least one standard deviation by hand. So if it does look like something that isn't too bad, I would recommend following along. So first in the leftmost column, I put the values from high to low. This isn't something that you have to do, but I do think it helps in understanding exactly what standard deviation is trying to say. So in the second column, you find the difference between the individual value and the mean that was calculated. So this was calculated in the previous section, but I did include more decimal places here because ideally you do not want to round until the very end of a problem. So when we talk about rounding a mean or a standard deviation to one decimal place, it's really not until the very end of the problem that you want to finally do that. Additionally, this is going along with the formula for standard deviation. So when we get the formula, when it pops up, I will discuss how this is following the formula. So the difference between each individual value and the mean shows how far away that value is from the middle of the data set. So it does matter that the value comes first, but in the third column, we do square that number. So overall, it does kind of cancel itself out, but we want to do the value minus its mean. So the middle of the data set at 36.429, these values, if they are from high to low, are going to span from being far away and closer to the mean, and then again getting farther away in the negative direction. So 40 is getting closer, so that difference is going down until as we scan through here, 36 is a little bit less than our mean of 36.429 by negative 0.429. So this third column takes each of those differences and squares them. So 7.571 squared is 55.190041, and I didn't round. I'm not going to round until the very end. And so what squaring these values does is it makes it so that if you have values that are a lot higher than the mean and values that are a lot lower than the mean, they don't cancel out. So you square them to make sure that you are describing how every value differs from the mean in total instead of just showing how the values that don't cancel out differ. So as this formula suggests below, we're going to eventually take a square root, but we want to work from inside out. So I'm going to start with the numerator, which is what the columns to the left have done. So what this sigma means here is it means the sum of. So this wants us to take the first x value, the first value, 44, subtract it from the mean, and then square it. And then take the second x value, subtract it from the mean, and then square it, and so on. So after doing that, the sigma on the top means the sum of. So at this point, we want to add up all of these values in this column here, which is 171.714287. So again, I'm not rounding until the very end. So I'm going to keep all those digits until I absolutely have to make my number inaccurate. And again, technically, since we rounded the mean, we're kind of already slightly off. But 3 decimal places is pretty good for this data. On the bottom, it is n, which is our total sample size of 7 minus 1. And then divide those two numbers and take the square root. This ends up getting you a standard deviation of 5.3 degrees. So degrees is the original unit of the data, and there's 1 decimal place since our original data is whole numbers. So what I'm going to do is I'm going to open Stata, and I'm going to leave this slide here. So I already have Stata open on the side here. And again, there will be a second video that will talk about what we've covered in this slide, as well as making graphs and other issues that you can run into when inputting data and other things that you start with when you're using a new software. So if this video doesn't have all of the answers to your questions, check out that other video first and then feel free to email me. So what we want to do is put our temperature data into Stata. And to do this, you need to open a data page, and you're going to do this by going to Data, Data Editor, and then Data Editor again. And so these are the instructions that I have on the slide. So when you open the Data Editor, a second sheet is going to appear. So I'm going to have this second sheet be to the right so that I can find my original data. First, what you want to do, though, is set up your variable. This is a step that you can skip, but I don't recommend it. It's really important in staying organized, which is definitely something that you're going to want to make a priority to do. So I want to name this column that I'm going to put my data in. So I'm going to double click on the column header, which is this top row here. So if you're using the arrows to scroll up and down, it's going to stop right here because this is the point where your data will stop and your labels will start. So when you double click on that column header, it's going to open a window, and this window is going to have a few things that you'll have to do. So the first is you're going to name your variable, which in this case is I'm going to label this. Let's try something that's not going to work here. So if you call your variable high temperature, and then this is the box that you want to select because you want to enter in your data manually. It will default to this in the future if you haven't closed Stata. If you hit OK, it's going to get mad, and it says the variable name you specified is invalid. This is pretty typical with a statistical software because spaces and variable names are usually not okay because it wants it to be one continuous flow of values, or characters in this case. So now that we've fixed our issue, and you will get a lot of pop-ups with Stata telling you that something has gone wrong. This is very common, and troubleshooting is something that you will have to get used to with any software at all, no matter what it is, statistical or not. So when you hit OK, your label goes up on the top. It has a little squiggle here because the column is not wide enough to display the whole label. But if you go to the bottom right, it gives you this really nice variable description. This is not something that all softwares have in this manner, and I do really like how the Stata does this. So now we want to enter in our temperatures. Sometimes we will be opening data sets from files, and other times we'll be typing them in by hand. And there will be a separate instructional video on how to open data from a file. So what I did to enter the data is I just started at the cell right below the label. I typed in the first temperature, and then I hit the enter button. So I did 29, enter, 30, enter, and then I went until I had all 7 values. It is very important to double check your values that you've entered, especially if you do this by hand. Think about how often you are sending a text message and you have a typo and it does some kind of autocorrect or it underlines in Microsoft Word that you have some kind of error. The same thing will happen when you're typing in numbers, but it's not a word that you recognize. So if you accidentally put in 92 instead of 29, it's pretty likely that you just won't notice it because it's not a word that you're looking to enter. It's just a list of values. So now to find the standard deviation in Stata, we're going to go to Data, Describe Data, and then Summary Statistics. There are different ways to perform functions in Stata. There are drop-down menus, and then there's actually a way that you can type in a command programming style. So drop-down menus are definitely going to be the most straightforward, but we'll see there's going to be a few cases where we'll have to use some commands. So in summary statistics, you have to do a few things here. So the first is you need to select the variable that you want it to work with. It's very possible that you could have a number of different variables in one data sheet, and so you need to make sure you tell Stata which one you want it to analyze. Oops. And see, here's a good example. I accidentally clicked this twice. So it will do an output, 2 different output menus of the descriptive statistics for high temperature since I had selected it twice. So we only need it one time, so I'm going to just get rid of that. And then I would suggest clicking on Display Additional Statistics. If you do the standards display, it's going to give you just the mean and standard deviation as well as the sample size. In the future, we're always going to want to select this one, so I would just recommend getting used to selecting this option from here on out. So then hit OK. And it looks like nothing happens, but the output that you get is going to come up on your other screen. So with Stata, you'll always have 2 different screens, your data screen as well as your output screen over here. So looking at the output screen, I have a number of different things that have come out. And right now, the only thing that we want is the standard deviation. So I'm going to move this back so I can compare this to the standard deviation that we found here. So 5.3 degrees, 5.3 degrees, so exactly. Even though we rounded this mean a little bit within our calculation, we still are accurate to 1 decimal place. So we're going to get a chance to do this again with example 2. So suppose a warm front came through and the new high temperature for the 7th day is 60 degrees. So this makes the temperatures 29, 30, 36, 40, 44, 38, and 60. So this is going to get us into, again, that idea of sensitivity to outliers. So find the new range and standard deviation using Stata only, no more by hand, and then describe how they have changed with the addition of the new high temperature. So the range is going to change in that the new high of 60 is going to be our new maximum. So now instead of a range of 15, we have a range of 31 degrees. So this is a pretty big difference if there was a temperature today that was 31 degrees higher tomorrow. The standard deviation that we will end up getting is 10.5, but I would like to again go through how we would get this in Stata. So going back to the data sheet, we don't need to enter in a new data or new column. All we need to do is just change this final 38. So to do this, you'll have to double click. So a single click or it can come up here, or a double click, which will get you to automatically be able to edit. And so I'm just going to change that number to a 60 and hit the enter button. So just as we did before, we want to describe the data, and then we want to do summary statistics for that. When we hit OK, it's going to still use the same settings that we had last time. That same exact variable, it's going to update with our new addition of the 60, and we want display additional statistics. So when you hit OK, it's going to output on the other screen. So here we have 10.45, which rounds up to 10.5, so that's exactly what we've got. So the next example is finding the mean and standard deviation of a frequency distribution. So finding the mean of a frequency distribution is new. We didn't talk about it in the previous section. So we're going to do one of them by hand, finding the mean, and then we'll just have the standard deviation from Stata. So this data below is the number of pets that they were had in a certain neighborhood. So to read this, if we just ignore this final column for right now, the number of pets, there was 4 houses that had 0. There was 12 houses that had just 1 pet. There were 8 houses that had 2 pets, and so on. So back in the previous section, there was a formula for finding the mean of a frequency distribution, and this is the sum of all of the class midpoints times its frequency divided by the sum of the frequencies. So we don't need to worry about midpoints here because we don't have a span here. We don't have 0, 1, 2, 3. We have just a single number. So we started off with a nice one. So we don't have to worry about those midpoints. What we do need to find, however, is the frequency times the value. And what this is doing is it's basically saying, okay, this data set could be 0, 0, 0, 0 for four zeros, 12 ones in a row, 2 8s. So the frequency distribution takes a big list of data and it kind of simplifies it together, makes it a little bit more compact. So Stata is actually going to show what this what it would have looked like if we had the data set all expanded. So according to the formula, we're going to add up all of the class midpoints or values. So that's going to be 0, 12, 16, 6, 4, 10, and 6, and divide it by the total number of values that there are. This is actually the same exact thing as finding a regular mean, since we don't need to use an approximation for the classes. So this is a frequency distribution where our classes just have a single number instead of a span of values. So that division gets us 1.8 pets. And so now here are the Stata instructions, and we're going to open new data and then follow those instructions. You can do a few things. If you want to delete this entire variable, you can click up on the top column header and hit the delete button, and then it says, "Are you sure?" And then you can say yes. It's pretty handy to know how to delete a whole variable because sometimes it's going to get unhappy for a number of reasons, which the other video will show. And if it does, you might just want to start over. Sometimes that is easier. So what we want this to have is the frequency distribution minus this final column. So this column isn't going to be something that appears, it's going to be something that you would calculate. So I'm going to call this number of pets. Again, we cannot have any spaces. And this bubble needs to be checked so that we can type in our own data by hand. I'm going to name the second column as frequency. And that's going to be how many of each number of pets the households had. So I am going to enter in the number of pets on the left column and the number of households that had those number of pets in the right. So you may need to pause this. I don't really want you to watch me type in the data slowly. So if we want to find the mean and standard deviation of this in Stata, we actually need to use the command menu. And again, we'll need to use this a few times. And so the command menu also has everything that you've done, including typing in values. So this can be handy sometimes if you can't remember something that you have done, or sometimes it can help you catch mistakes. So in this command line, we want to type expand, typed correctly, not as my original typo had. Expand, and then the variable that has your frequencies in it. And it needs to be case sensitive. So let me mess up here. And what happens is it says frequency not found. That's because frequency with a lowercase f does not exist. So if you've done programming in the past, you will be already familiar with how specific you need to be when it comes to agreeing with everything. So when you type expand frequency with a capital F, what it does is it takes the number of zeros that you had, and now there's going to be 4 of them total in this row. So the original one stays, so I'm going to highlight those. So there's a total of 1, 2, 3, 4 zeros. There's going to be a total of 12 ones, 8 twos, 2 threes. We don't need any more 4s because we need 1 and we've already got one up here highlighted. 1 more 5 so that we have 2 altogether, and then we don't need any more 6s. So this takes your data and it puts it back into what it would have looked like before you had it in the frequency distribution. So just as we did before, we're going to find the mean, and we're going to use the number of pets column. So temperature is still going to be in there. You can delete that out. If you leave it in there, it's going to get mad because that variable doesn't exist anymore. So we wanted to say, hey, what is the average number of pets per household? So that's the variable that we want to have in for the analysis. We still want display additional statistics, and then we want to hit OK. So we end up getting a mean of 1.8, which is what we had found before. And the standard deviation, which we did not find by hand, although we could have using the same process that we found in example 1, that's 1.5 pets. So I had previously gotten this answer from Stata. I definitely didn't do this one by hand, although we could have, but depends on how bored you are. So for the second example, it's going to be pretty similar, except for instead of having just a single number in our class column, which is what these are again in a frequency distribution, we now have a span of numbers, which is pretty typical for the data that we'll be looking at. So what we want to do is we want to take the frequencies that we have and calculate how many of them we'd have from 10 to 19. So when we had this original data, which by the way is the high temperatures for Casper, Wyoming in 2015, it was every single day except for December 30th. I did compile this data myself, and for some reason December 30th just didn't have any temperatures. So I broke these down into classes based on the high by tens. So there was 12 days in 2015 that had a temperature of 10 to 19 degrees. However, we don't know if there was 10 days that had a temperature of 10. We don't know if there was 10 days or 12 days that had a temperature of 19. So what we do instead, if we don't have our original data anymore, it's completely gone, we use the class midpoint. And we use the class midpoint of every single class. So instead of saying there's 21 20s, 20 highs, or 21 highs of 29, we just say, hey, we don't know the original data anymore, so it would be best if we use just the middle value. So again, when we put this in Stata, you can completely delete the data that you have. You can open a new data sheet, which is what we're going to do right here. Or you can keep on adding columns to your existing data set. It depends on your style. I usually try not to add too many variables to a data set. It can end up causing confusion if any of the variable names are similar. So it says, do you want to continue and lose any unsaved data? So I'm going to say yes here. And now I'm going to type in a temperature variable and a frequency variable. So I'm going to again put the temperature to the left. Even though the midpoint comes in the rightmost column, we are using this to describe this span of numbers. So I like to keep the classes on the left always. And so this isn't the actual recorded high, I believe. I think this is the predicted high temperatures. So I type those frequencies in pretty fast. I'm going to double check them. And I'll do this every time, not in the video, but I'll always pause the video and double check. And so again, I wanted to have, instead of just that there's 12 14.5s, 21 24.5s, I wanted to just give me one list of data. So this is going to be, again, expand frequency. And it takes us, so now there's going to be 12 14.5s here somewhere. And so now we want to find the column of the mean of the temperature column. I'm going to check and make sure it worked out. The only way I can do that is there should be 364 numbers, because again, we were missing one of them. So, describe data, summary statistics, and now number of pets is still in there. I'm going to select temperature from my drop-down. And everything else in here should be okay. So from what I found previously, the mean high temperature for Casper for 2015 should be 61.3 degrees. There we go. And the standard deviation is 21.8 degrees. So this is a pretty high standard deviation, especially compared to the data set with the Oscar winner ages. So in general, we're varying pretty far away from the mean of 61.3 degrees. I'm going to make a graph of this really fast, and again, there will be more information in the video that's for SPSS specifically. So the graph menu is going to give you an option of the popular graphs that we've looked at that are in the first 4 sections, or 3 sections. And I'm going to make a histogram of this really quick. So making a histogram is going to give you a lot of options, but for the most part, you can ignore them unless you want to make a pretty custom graph. So select the temperature variable and then hit OK. And we're not going to worry about labeling this too strictly. So this is an example of a histogram that's going to need some work to it. So I just wanted to get an idea of how the spread of this data was. So we got a lot of gaps in between here, and that's just because of the way that the data is set. So looking at this, definitely we're pretty far spread out. We go below 20 and close to 100. So compared to the previous data set, we definitely have a large spread here. Okay, so let's keep going with the slides. So we have a few rules that are going to take what we know about standard deviation and bring them together with the mean. And these are going to be really important because it's going to help describe how a single variable lives inside a data set. So our first rule is the range rule of thumb, which states that a value is considered unusual if it is more than 2 standard deviations away from the mean. So I have a number line down along the bottom, and we'll see this again. We'll create some of them ourselves, where we have the mean in the middle, and think of it like a staircase, where each step to the right adds a standard deviation, and each step to the left subtracts a standard deviation. So also there are arrows at the end of these because in theory, we're going to consider every single value from negative infinity to infinity, even if it's not possible. We will talk about why this is okay as we go on, but every time we look at a data set, we consider that the values could take on negative infinity to infinity. So we'll look at an example to practice one of these coming up. But similar to this, we have the empirical rule. And this is, again, it goes hand in hand with the range rule of thumb. And the empirical rule states that for data that is approximately normally distributed, which again is our bell curve shape, about 68% of the data will fall within 1 standard deviation from the mean. About 95% of the data will fall within 2 standard deviations from the mean. And about 99.7% of the data will fall within 3 standard deviations from the mean. So let's look at a picture of this to kind of make sense of this. Oh, and in Unit 3, we'll be able to determine these percentages exactly. So we'll have a way where we can determine to a lot of decimal places. Is it, 68.22554? We'll be able to see exactly what those are. So here's a picture of the empirical rule along with the bell curve. So about 68% of this data will fall within 1 step above and below. So 1 step above, 1 step below. And what you want to think about is this whole curve underneath it is 100% of any values that can occur, because again, this goes from positive infinity to negative infinity, even if it's something like dollars spent at the mall. So there's going to be a center amount that people will spend on average, but this is going to go from positive infinity dollars to negative infinity dollars. And there's always a difference between theory and reality, but the actual math behind it doesn't make too much of a difference, surprisingly. So within 2 standard deviations above and below is about 95% of the data. And then finally, within 3 standard deviations above and below is 99.7. And these are approximate, but they're pretty close. So they're definitely not off by more than a 0.5%. And we'll see coming up what those are. So here's another breakdown of the bell curve. It's the same percentages that we looked at. Those are shown on the bottom here. But it takes each of these pieces in a geometric sense. So just like a regular geometry, if you were to split a square in half, each side would be 50%. So it's the same even though this is this funky bell-shaped curve. Within 1 standard deviation above and below, it's 68%, which means if we split it in half, that each of those pieces would be 34%. One more to the left and one more to the right is going to be 13.5% each. And this is because this whole section here, the green and purple together, is 95%. The middle section is 68%, the purple, and so that leaves 13.5% in the green area. And then lastly, this is 2.35% on each of these pieces for the same reason as described for the 95%. And there's a little bit of this curve left on each of these sides. So that may be something in the future that you might have to answer. So we have a few examples left. This is definitely a section in class that will take more than 1 class day, so that's why this video is a lot longer than most. So the first question is, IQ scores have a normal distribution with a mean of 100 and a standard deviation of 15. First, fill out the normal distribution using these values. IQ scores are definitely something that follow a normal distribution. So if you took everybody on the planet and found their IQ score and put it into a histogram with a really small class width, let's say we just did a class width of 1, you would end up with something that is so close to a bell curve shape that, I mean, it's completely surprising to me. So to fill in these values along the bottom, our mean of 100 goes right in the center. And then each step is a distance of the standard deviation. So each step is 15. So one step up is going to be 115. One more step up is 130. One more step is of 145. There are more standard deviations here, but we kind of stop because there's not many people that have an IQ score of over 145. So in general, we will stop at 3 almost always. But they keep going. We just, we don't need to focus on them. Going down, 100 again is in the middle, and each step takes away 15. So that's going to be 85, 70, and then 55. The following slide has a few more questions for this example. I would pause the slide and use the empirical rule to answer these 4 bullets. So for the first bullet, what percent of the IQ scores fall between 70 and 130? So 70 is 2 standard deviations below the mean, and 130 is 2 standard deviations above the mean. So by the empirical rule, we're going to have about 95%. So basically what this is saying is that 95% of the entire population will have an IQ score between 70 and 130. Approximately what percent of IQ scores fall between 85 and 115? So this is 1 standard deviation below and 1 standard deviation above, which by the empirical rule is 68%. What percent is between 100 and 115? And so since we have 68% in this section from the second bullet, there's going to be 34%, exactly half of that in the 100 to 115 portion. And then lastly, approximately what percent of IQ scores fall between 85 and 130? So this is 1 standard deviation below and 2 standard deviations above. So we know for sure it's going to be more than 68%. And then using one of the empirical rule pictures or by hand, you can calculate that this piece is going to be 13.5%. So 68 plus 13.5, 81.5% in between those values. The next question, the lifetime of a certain battery is normally distributed with a mean of 40 hours and a standard deviation of 3.2 hours. Determine the minimum length and maximum length that are usual for the battery's life. So when you're talking about minimum and maximum usual length, you want to think about the range rule of thumb. And the range rule of thumb says that the minimum value is going to be 2 standard deviations below the mean. So I subtracted 3.2 off from the mean of 40 twice, or 40 minus 2 times 3.2. That's going to be 33.6 hours. The maximum battery life is going to be 2 standard deviations above the mean. So you can either add 3.2 on twice, or do 40 plus 2 times 3.2. That's 46.4 hours. So this is 2 above and 2 below, so if we combine this with the empirical rule, this would mean that about 95% of batteries would last between 33.6 and 46.4 hours that are of this type. So it's of this specific certain battery. Our last example here, this is a made-up example. At the New Age Information Corporation, the ages of all new employees hired during the last 5 years are normally distributed, which is very possible to be the case, but it depends on the position or the field. Within this curve, 95.4% of the ages centered about the mean are between 24.6 and 37.4 years. Find the mean age and standard deviation of the data. So a few things need to happen here before you just start plugging in numbers into the bell curve. The first is that it's normally distributed, so that's why the bell curve is even here. If it wasn't normally distributed, we didn't know it was, we couldn't use the normal curve. Secondly, they give us two values that are centered around the mean, and they also happen to have 95-ish% of the data between those two values. So this means that we can use the empirical rule. Even though this doesn't say 95 exactly, this is, again, the empirical rule is an approximation. So it's pretty close to 95. So the next slide has a picture that I've used. I would recommend trying to figure this out first before you just look at my solution, because there's a lot of different ways that you can think about this one. So I'd say there's at least 3 different ways that I can think of that somebody might approach for this problem. First of all, I would find the mean, but you could technically find the standard deviation first. That is up to you. The way I thought about this was that this distance to the middle from the 24.6 is the same as this distance from 37.4, if we think about this in a geometric sense. So I just found the average of these two numbers to get 31. So because that's right smack dab in the center where our bell curve peaks here, that's going to be the mean. Now once you've done that, you can find the midpoint again and then find this distance. Or the way that I looked at this problem is that this was 6.4 across, so that meant that each of these steps had to be 3.2. So I will show you, I would definitely check myself on this one. So I would start at the lower number of 24.6 and add the standard deviation twice and make sure I get the mean of 31, which we do get that here. And then I would take one more step and then one more step again and assure that I get this upper number here. So that is a good way to check yourself and make sure that you are correct with this problem. There was a lot of material that was covered in this section. Introducing Stata is probably about a third of what this topic ended up discussing. I would definitely make sure that you start going through the examples on your own outside of the videos to ensure that you could do this independently on a quiz or a test. So please feel free to email me if you have any questions. I definitely recommend checking out the Stata video so that you get a chance to see some more details about the kind of errors that you can run into while you're using Stata.